Hey, John, it's easier to go straight across. That was fun. Well, I haven't had any trouble. Okay. I have a tough time walking up there.
The sampling time used up, it was time to return to the rover and head back to the lunar module.
And they did it in 2 minutes less travel time than they were pre-planned. Fantastic.
Tony, how about an extension, you guys? We feeling good. Is that all we're going to do tonight was sit around and talk?
But with the limited oxygen and water in the backpacks, it was finally time to close out EVA-2.
Okay.
Now I think they realize that it's not more, well, a gee whiz, like my friends say, thrill, but it's real exploration, and this is much more serious and much more important for the future of mankind than just a plain exploit, a technical or technological exploit. This is exploration.
Ray Bradbury claims that what mankind sees in the exploration of space is his first chance at immortality since he invented religion.
That about gets it.
April 23rd.
Okay, fine, Tony.
The decision had been made not to try and fix the broken heat flow experiment because of the time and complexities involved. Traverse number 3. Today, Young and Duke would head north about 5 kilometers to North Ray Crater, the largest lunar crater to be sampled by men.
Outstanding.
Okay, Tony, it seems to me this is a more subdued surface over here than going towards South Ray. Oh, spectacular. Just spectacular. Wow. Sorry, Charlie. Beautiful. I got to keep my eye on the driving. That's great.
Jack, that's a good point to remember. All 3 crews now tend to think they're there before they get there.
I remember.
Man, does this thing have steep walls. They said 60 degrees. Now, I tell you, I can't see to the bottom of it, and I'm as close to the edge as I'm going to get. That's the truth.
Now the routine, if anything on the moon can be called that. Test, collect, photograph. Keep moving. Time is precious on the moon.
The crater, they look like drill holes is what they look like. You do that in West Texas and you get a rattlesnake. Here you get permanently shattered soil.
How about rolling that one over?
No way.
Then, one of the most spectacular discoveries of the mission.
Look at the size of that biggie. It is a biggie, isn't it? It may be further away than we think. No, it's not very far. It was just right beyond you.
And we better press on for the big boulder?
Can't blink too dirty. Okay, we're headed that way. You get the tongs, John? Yep, we got. I'll carry the rake.
That big black dot.
Fantastic.
Like right here.
If we could see to the bottom, we could say for sure if this big black rock is right out of the bottom. But my guess from the old photographs is it probably is.
Okay, that sounds like a good guess.
God, you mean they weren't at it? No. It looked like they were standing right there.
Look at the size of that rock.
I'm curious what they're going to look like when they stand next to it.
We can see. The closer I get to it, the bigger it is. Yeah, but look at the permanent shattered part, Charlie. On this side over here? Yeah.
And as our crew slowly sinks, we bet upon disappears into the sunset.
Well, Tony, that's your house rock right there. Very good. Don't get too near the edge of that thing. It falls off. Look over at your right. It falls off pretty good. Yeah, I know.
Yeah,
Keep going.
Can't believe it. I can't either. Okay, let's go on back. I am. Be right with you.
And we encourage you just to look for some variety.
But now it was time to head back to their base and close out the EVA.
All right, we think you could just about head south now.
Yeah, the only reason.
That's it. We're going home again, jiggity jig.
During the previous EVA, a section of a rear fender had come off the rover, causing the astronauts to receive occasional showers of lunar dirt.
And that's a beautiful sight.
Young parked the rover, then moved out to join Duke, enter the lunar module, and prepare for liftoff.
Boy, Houston, the beauty of this place is absolutely incredible.
Smile, FAO. Don't be mad. We'll get it up there. See how nice and leisurely it's been? That's the way it should be, getting ready for ascent.
10 seconds.
What a ride, what a ride. Pitchover's on time.
Together in orbit, the two spacecraft pirouetted, each inspecting the other.
This is one of the fastest maneuvers I've made in a long time.
The inspections complete, the command module and lunar module maneuvered to docking. John Young, Ken Mattingly, and Charlie Duke, reunited aboard the command module, settled down for tomorrow's tasks. Jettison the lunar module and burn out of orbit to come home. April 25. Ken Mattingly left the confines of the command module cabin, 173,000 miles from Earth. As he orbited the moon, he had not only made visual observations, he had been operating a complex series of experiments. Many of these had returned instant data to Houston. Two had taken thousands of high-resolution pictures of the lunar terrain. Now, Mattingly retrieved the film canisters and made his way back to the cabin with them, as Charlie Duke stood in the hatch to help him. It had been quite a mission. In John Young's words,
I think we've seen as much in 10 days as most people see in 10 lifetimes.
April 27, the last day. The crew looked out their windows through the 5,000-degree fireball of re-entry at their native planet.
Recovery, this is Apollo 16. Apollo 16, this is recovery. Welcome back, go ahead.
That is beautiful, isn't it?
Now they're blooming. Beautiful. There they are. Beautiful.
Apollo Control Houston, an observer on the Ticonderoga estimates the distance from the ship about 1 mile.
Just got it on in service.
You saw an example of goal-oriented teamwork in action. The kind of thing that made this country great and the kind of thing that's going to keep it that way.
Real smooth shot. Every bit of it, Jerry.
You brought them in beautifully. Well done, young man. Outstanding.
I cannot touch that cigar anymore. I cannot.
I told him they're going to improve the skyline. We're in trouble.
Mike, congratulations. Well done.
Yeah, we get one more.
Well done.
One more to go. I just hope.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
The laser, a useful tool in industry, science, and medicine.
When it comes down to it, a laser is just a light with extreme focus. It's both elegantly simple and extremely complicated. And it changed the way we literally see the dimensions of our Earth, our moon, the planets, asteroids, and beyond. But it was a long road to get there. Back in the 1980s at NASA, using lasers to measure physical features from space was too experimental, too risky. Fortunately, it was also a time of change and risk-taking at Goddard Space Flight Center.
In the 1960s, there was probably not much question that when a science or applications mission came up, for the most part, it went to Goddard. And we've got to do a better job of selling ourselves and being sure that we're responsive to what headquarters is looking for in terms of the competition between ourselves and other NASA centers.
I came here as hired by the center director, Noel Hinners, in '85, and he said, so what do you want to do? I said, I want to map the topography of Mars, at this scale, not the scale of buildings. How do we do that? And he goes, well, we got folks, they do stuff. And so I met a few of them very quickly, and that was Jim Abshire, John Degnan, Jack Buffton.
We started working with laser remote sensing instrumentation. It was the same type of instrumentation that communicated from ground to satellites in satellite laser ranging. We could do a little airborne laser remote sensing, and Garvin and I sort of found each other through that. I said, come on down to Wallops and we'll fly this. And he said, oh, topography, Earth, yes, I want to measure it.
We literally took a T-39 training aircraft that was put together by the Wallops team, really impressively, and bolted in a big telescope with a laser and went flying out in northern Arizona, where I had done some field work. So out there we have Meteor Crater, we have volcanoes, and we have the Grand Canyon, and the Painted Desert. So we figured in one place we could study all this.
And it was on the strength of that Jim Garvin became interested, and it put him in a position to, when Dave Smith found that his radar altimeter was canceled because it was $30 million instead of 10.
They kept talking to me about, look, we're really close to getting a laser altimeter working. And I've been in lasers actually for 20 odd years before that, if you know what I mean, but laser ranging from the ground to spacecraft. So I was very familiar with the lasers, and I wasn't averse to it, on the contrary. But NASA offered me the situation that said, look, we've got a certain amount of money for you. We're willing to spend $10 million on this instrument. But there has to be some sort of competition. You need to choose which instrument you would like to fly to measure the altimetry.
And there were 4 candidates. 3 of them are radar, and 1 the laser that we call MOLA. There was no one in their right mind that would bid a laser altimeter. Seriously. And I was all gung-ho. I was a young guy, no gray hair. There was a lot of reticence. There was so little trust that this could be done. NASA has made a monumental achievement in both radar and visible near-infrared imaging of the surfaces of Earth and other planets. But those are flat field views. And the missing dimension, the hidden dimension, which drives where energy goes, where the water flows, stability of landscapes, is the third dimension. We take for granted the map. Sometimes you need the map to do what's beyond the map.
Making those maps with that crucial third dimension is what laser altimetry, or LiDAR, is best at. And over the decades, Goddard's gotten pretty good at explaining just how laser altimetry works.
This is a laser altimeter, and what it does is it sends a short pulse of light
from a moving platform that's observing a surface, an airplane, a satellite.
Gets a reflection straight back off the surface.
We record that reflection and the time very precisely.
Of the pulse from the spacecraft down to the surface and back again.
Which allows us to measure the range to the surface.
When that's done repeatedly in orbit, you can build up a map.
The fast rate of light pulses and the small footprint allow LiDAR to measure with a much finer scale than traditional radars.
They had a big review, and the leading radar guy that had flown radars to Venus, Gordon Pettengill, at the end said, well, I don't know about you folks, the laser's better.
In time, Goddard would become a leader in LiDAR, in mapping our Earth and planets with unprecedented precision. But for now, they had to actually build the first one.
The requirements were, of course, we were in a much higher orbit. The orbit was faster than going around the moon, so we needed a larger telescope. We needed a more sensitive detector. We needed more laser energy. So in order to put our concept together, we had to gather a team. And then we had to convince their management that this was not a crazy idea and that we actually had a realistic chance of making this happen.
We worked a lot of hours. I can remember Jim talking about, working 10-hour days, and I was doing about the same. But, it really didn't matter because it was so exciting to be working on something that was going to actually map Mars.
I was fresh out of getting my master's degree in computer engineering. I was young. I had to really dive in deep. I had to spend about 2 years working with the team on algorithms. How are we going to find the surface of Mars? How we're going to track it? How we're going to compute all the precise ranges?
And we were sort of making our way. We were defining the rules as we went.
We finished the instrument pretty much on time, and certainly as they said in the letter to me, look, if you don't make it on time and in budget, we will fly a brick instead. Okay, we're not going to hold this mission up. I knew about planetary missions. They have to go within certain windows. But anyway, we made it all right.
5, 4, 3, 2, 1. And liftoff of the Titan III rocket with the Mars Observer and America's return to the Red Planet. And the vehicle has cleared the tower.
We've got X-band launch at Canberra. Yeah, all right.
Roger, I have that report. Very happy crew. And Mars Observer is on its way to Mars. Trajectory is right on the money.
We've assumed that the spacecraft properly executed its orbit insertion sequence, and we presume the spacecraft is in orbit about Mars, but we have no positive confirmation of that because, as for the last 3 days, we have no communication with the spacecraft.
To say you simply don't know what happened, it could be in orbit, it could have flown past the planet.
What are the scientists doing to relieve the tension in there?
Screaming loudly, probably.
We still don't have communication with the spacecraft. However, we are very hopeful and we're cautiously optimistic that communication
every day, will be in fact,
restored.
Without communications clearly lessens our probability of success.
You say, though, we give up.
We have not given up.
On 21 August 1993, a tragic event occurred. Communications with the Mars Observer spacecraft were lost during a sequence referred to as the pressurization sequence. This was a sequence in preparation for insertion to orbit about Mars.
Once again, I mean, we're always trying things because they're hard, not because they're easy. And so once in a while, we're going to have a failure because we are trying hard things.
But I had been fully anticipated that we could have problems with this instrument. This was a new ball game completely, okay? But I was not concerned about the spacecraft. It never crossed my mind that spacecraft would let us down. And so this was a blow in the sense of, wow, something I completely didn't expect.
You know, we held out hope for a while that maybe it would come back, maybe they'd find it or recover it or something, and then eventually that settles down and you realize the mission was lost.
I was devastated. I think we all were, and it really wasn't clear at the time whether we were going to have a follow-on to actually do what that mission was supposed to do.
So that was extremely hard to take. What made it easier is the amount of time we had for grieving was actually pretty short.
NASA decided that we want to continue this and go back to Mars. And so we had to snap out of it, literally, and get back to thinking about and fighting for the next mission, which is Mars Global Surveyor. It was a difficult time, and it was the first time I think I really felt I had to get in there and argue with my colleagues, but as the PI, it was particularly for me, that we needed to get back to Mars and we needed to get back with this instrument. Knowing that they couldn't carry all 6 or 7 instruments, only 4 would go, the laser altimeter had to be one of them, okay? The engineers had a chance to kind of just not change it, but just do some things a little bit better.
That's what engineers like to do, is they fix all their first round mistakes in the second round and make new ones.
We were asked immediately, how long will it take you to rebuild another copy of MOLA? How much is it going to cost? Can you get your team back together in time? Do you have the parts? So there was immediately a flood of things we had to do.
Jim Etcher brought me in for the detector engineer who just left the Goddard at the time. So I was lucky to join the team working on the detectors. We were only given, I think it's 3 years to rebuild it. It's shorter than usual.
And everyone, all the management knew that means there's no wiggle room really in your schedule.
But the team was largely still there, and everyone is geared up to redo it since the first one didn't make it. So everyone really wanted to do it again and do it right.
While the Goddard team was building MOLA 2 for the Mars Global Surveyor mission, a small team seized a long-awaited opportunity to hitch a ride on the space shuttle with an experiment known as the Shuttle Laser Altimeter.
I think confidence comes from demonstration. Sometimes you have to do more. Sometimes you have to do less.
Working personally to build that instrument, we built it at Goddard in our lab down the hall without any fancy paperwork or flight procedures or anything. We just built it.
I was hired then to come on board working on the shuttle laser altimeter, and I was brought in specifically to work on precise positioning, precise pointing, and precise geolocation of the surface footprints.
And we tested it on the roof, shined it over to a bank building 11 kilometers away, lined it up, and it was ready for the shuttle.
It was a Hitchhiker Special that we flew with help from NASA headquarters on the Space Shuttle Endeavour.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
Throttle down as the orbiter prepares to pass through the area of maximum dynamic.
They turned it on for us, and the first time they turned it on, the shuttle's upside down with the laser pointing at Earth. We're over the middle Pacific.
First light showed all this fuzz over the surface of the Earth. We're all looking. We thought we got something wrong. We realized later we were seeing the boundary layer clouds over the ocean. When we came over land, the fuzz was the height of the trees.
All of a sudden, the laser pulses got shorter and shorter distances.
The first landfall of the shuttle laser altimeter in the first orbit went right over the summit of the Mauna Kea volcano in Hawaii. Well, we're extraordinarily delighted to report that the shuttle laser altimeter experiment, it's a hitchhiker experiment on STS-72, has performed absolutely nominally. In fact, everything has worked even beyond our expectation.
And that was a genuine first light experience with MOLA technology, but on Earth.
Really had to get those data sets out there, and you had to get a couple people that really bought into it and built on it and convince others that this worked.
As the data from the shuttle laser altimeter began to convince some skeptics, the Goddard team finished the MOLA instrument. Again.
Our MOLA team really came through. It was just really another great experience for many of us, including me. We were able to deliver to the Mars Global Surveyor project, and it got launched.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the red planet.
6 solids.
And when Mars Global Surveyor started getting closer to Mars, we were going to go into this aerobraking phase. That was an opportunity that we had to go ahead and turn on the lasers and see if we could track the surface.
Somebody being carried it for him.
And Station 45 was having problems locking up to the 2K data.
What was that? What you
said 1607 or 16?
Can you tell if MOLA has been turned off?
Right.
Copy, I'll probably kill my query and restart it as soon as that query is up and running.
That must be the nadir event.
I'm hungry. You didn't really want to sandwich.
Look at the laser coming back, Rob.
Greg says about 18.
This is going to be too fast and I got too much data.
Look at that. Yes.
Look, there's a little tiny terrace. This is the first profile of a crater we've ever seen on a planet.
That is.
Rob, nice laser.
Right.
We have Mars, finally. 12 years. All right, let's take a look. I don't understand.
Over a decade later, the Goddard team had proof. Planet-scale laser altimetry worked. It could map distant craters and valleys and mountains. It changed the game.
Today, we've ushered in a new era in the remote sensing of Mars.
And this particular data set that we've acquired has in fact enabled us to generate what we consider a very detailed description of the shape of the planet Mars.
This has significant implications for the flow of water early on Mars.
We believe this is one of the youngest features on the planet. We're seeing a planet that is very different from Earth. And it's telling us something about the Earth in an indirect way that says that not everything works in the way that we originally had in mind.
The kind of measurements that we're making now are allowing us to, characterize Mars on timescales of days to years now. And then the next step is to try to go back eons and try to figure out what changed on Mars.
I mean, at that time, we used to brag that Mars was mapped better than the Earth. The accuracy of MOLA was so good, and after a couple of years, the coverage was so good. It was definitely a more accurate map of a planet than any planet.
And this came out of it can't be done in the mid-'80s to a tool that we now accept as the standard.
For those of us that worked on MOLA, it was transformative. It wasn't at a destination or a place that we were as much as a place that we would become.
Following MOLA, in some ways we were in demand to consider whether we could provide a laser altimeter to another mission.
A few missions, actually. It was no longer a question of if LiDAR could work, but where else it could work. But as the opportunities to test the limits of LiDAR arose, so did the challenges ahead. The Goddard team quickly began to see the evolution of LiDAR missions, building on the successes of new frontiers mapped by MOLA.
We've measured the changes, the seasonal changes in the Mars ice caps, both the North Pole and the South Pole. We've measured the volumes, we've measured the mass that's involved in that. We now have a density. So now we know the kind of processes that are taking...
Dave Smith invited me to be on the MOLA altimetry science team. And that was because of my experience with using altimetry over land rather than ocean processes.
Zwally was an obvious choice to study the Martian ice caps for MOLA, given his decades of expertise with our own polar regions, studying the ice sheets of Greenland and Antarctica through the 1970s and 80s.
And then as we went into the 80s, NASA was sort of the beginning of the development of the Earth observations program.
So the Earth observing system, I think, will be the first effort targeted at looking at the whole Earth system as a system, rather than just the little components that make it up.
Somewhere along then, I teamed up with Jim Abshar.
Jay had been pushing for a long time for a dedicated ice altimetry mission, which turned into ICESat-1.
Designing ICESat-1 marked a major leap in what LiDAR needed to do and how challenging it would be to do it. To measure the changing ice sheets, the LiDAR had to be far more precise, cover the same tracks season to season, and it needed more power and a larger instrument, which meant much more time to build.
We built a simulator for ICESat-1 that allowed us to sort of figure out how precise it could be, how we would process the waveform data coming back, how we would track the surface.
This algorithm was much more complicated than anything I had ever worked on before.
But all this meant essentially for the ISAT mission, you needed a much more advanced version of MOLA.
In Mars, we really didn't know what was there until we got the measurements, so we were doing discovery. On Earth, we have to make quantitative measurements about what's happening.
4, 3, 2, 1. And we have ignition and liftoff of NASA's ICESat and ChipSat spacecraft looking at stars and ice.
But after, we'd worked on glass at that point more than a decade, and it already launched, and usually you think, okay, now we're going to be able to enjoy the data coming down, and what can we see in the data? But there was much more, what is this mystery we're seeing? Why is the laser energy going down? Things were not working the way we expected them to, and there were mysteries, and we weren't expecting, after MOLA in particular, to have mysteries at that point.
One of these unexpected mysteries came down to the wire. Several wires, actually.
What happened on glass was the laser diodes had gold bond wires and indium solder. If you bring these two metals together, even though they're not reactive, they do combine to form gold indide.
The gold indide ate away at the wires, leading to added thermal stress, and eventually the failure of the first laser. And the second and third lasers were degrading as well. Tough decisions were ahead.
When these missions operate, there's a lot riding on the missions. You don't want to make any mistakes. You want to optimize things as best you can.
The question was, given that we would have so much lifetime expectancy from the lasers, well, the scientific decision was that the best way to use that was to operate for periods of about a month and do that 3 times a year.
That decision paid off when ISAT showed dramatic change in land ice around Greenland, and it also proved that LiDAR could be used to measure something called sea ice freeboard, a major breakthrough in determining sea ice thickness and an essential science goal for the future of ice measuring satellites.
Even though the ISAT project required much more care and feeding, it really laid the groundwork for all the subsequent missions that Goddard has flown.
Around the same time that ISAT was developed, Goddard was tasked with designing a laser for measuring a place far from any icy poles.
Sean Solomons was the PI of Messenger, and he said, I've been asked to PI a mission to Mercury. I really want a laser altimeter on board. Can you make one that will work there? So the short answer seemed to be, yeah, I don't see why not, but there will be extreme thermal circumstances that we'd have to worry about.
That was a really tough one because you fly in close to the 800-degree planet and then you have a 12-hour orbit.
The temperature changes by tens of degrees in a few minutes.
It had to always shield itself from the sun constantly, which meant that in orbit it was often at a very high angle. It was a challenge to try to continually figure out where the surface of Mercury was.
And then they wanted to be small, much smaller than a mole. I think it's end up to a quarter or a fifth of the size.
But I remember the manager who was running it for us at the time kind of said, "You realize I've thinned every wire in this electronic package so thin that you better not look at it twice because it might break." But that's the level we had to go to get within the 7 kilograms, okay? And MLA was the laser altimeter that we proposed, and this was really pushed the limits of what we could reasonably expect to do.
Despite the extreme environmental gauntlet, the Mercury laser altimeter kept on collecting data for 4 years, right up until the very end when Messenger crashed into Mercury in 2015. But before that, it captured historic views of the planet's topography.
It is time for America to take the next steps. Beginning no later than 2008, we will send a series of robotic missions to the lunar surface to research and prepare for future human exploration.
And then one day, the president, I think it was George Bush, suddenly decided we're going to go back to the moon. Wow, all of a sudden, okay?
We've been thinking about putting a LiDAR around the moon for a long time, actually.
And I really wanted to have a crack at doing a good one instrument for the moon. I mean, my interest was in gravity and topography, two things that need to come together to measure the structure of a planet.
And then all of a sudden, we got a call from headquarters. Can you design a LiDAR around the moon to map the topography?
And so the instruments were chosen from proposals based on the ability to help select sites and determine the safety of landing in particular sites on the moon.
The LiDAR would be the Lunar Orbiter Laser Altimeter, or LOLA, and it marked another leap into laser altimetry.
We also came up with the idea of having multiple beams.
We managed to put 5 beams on the surface. And that kind of changed the observational strategy, if you know what I mean, of 5 parallel beams.
But after launch, Lola was suspiciously silent.
When Lola started, I think that was just devastating.
We didn't get any measurement at nighttime when we first turned on. It was quite a shock, and it was the first LiDAR that didn't work at the initial turn on.
The people that are heavily involved in the instrument development, you're pulled back in if there's surprises that occur.
On Lola, the blankets were all tied tightly to the beam expander and the telescope, and this germanium black kapton, which we didn't test with, was very strong.
And then we caused a misalignment.
I remember we discussed whether we wanted to check the alignment at spacecraft level, and we just decided not to do it. I think that was my fault, because we could have. We started in the worst possible orbit for that failure mechanism. And so we were out of alignment, and we had no signal at all, and that was just it was a tough couple of weeks.
Yeah, it is a lessons learned for life for me.
A couple of weeks later, we noticed a little blip at the South Pole, and so we had some hope. And it eventually just, as the orbit progressed, the signal kept getting stronger and stronger on the daylight side.
Despite a bumpy start, in time, Lola and the Lunar Reconnaissance Orbiter mission became revolutionary in mapping our moon.
And it's turned out to be exceptional in terms of describing the topography of the moon. As a result of Lola, I think largely, if not the others as well, the doubts about whether a laser altimeter, for example, could last, age limits, lifetime limits on the laser altimeter were dispelled.
The Cold Atom Laboratory is in many ways the coolest thing and the coldest thing we've ever done on the International Space Station. It is allowing us to investigate cold quantum gases and make breakthroughs in areas of physics that up until now have been unavailable to us.
NASA built the International Space Station to do the kind of research that we're doing in the Cold Atom Lab. This is the first time we're able to study this fifth state of matter in space.
Bose-Einstein condensation is an amazing feat of engineering in itself, but this type of physics is difficult to do in ground-based experiments, and so doing this in microgravity is going to allow us to really see what's going on. So you have something cool, how do you make it cooler? You put it in space.
Our ability to study cold atoms is really going to advance our knowledge in areas that will help us in quantum computing, quantum communications, and learn even more about gravity and how it interacts in our universe.
The Mars Polar Lander and Mars Climate Orbiter missions failed. We had to get back in the saddle. We had to get something landed on the surface of Mars.
I thought it was honestly like a crazy idea given the amount of time that we have. The probability of failure was unacceptable.
Engineers don't like designing when there are too many unknowns.
They fooled me into taking this job, saying that, oh, it won't be that hard. It's a reflight of Mars Pathfinder. You have all the pieces there.
We knew it would be a challenge, but I don't think we adequately assessed how difficult it would be.
I think in the back of your mind, you're always prepared for anything to happen, but this wasn't one of the places that we thought something would go wrong.
Come on, man.
You don't put a system like this on a major spacecraft like this at the last moment.
The trouble is, it's great on paper, but until you put it out there and test it, you really don't know what you have.
You know, I've told my people that in terms of my top 10 list of worries, the first 3 are schedule, schedule, and schedule, and there's nothing in fourth place.
I came to the realization that the heritage wasn't in the blueprints. The heritage was in the people.
Our next pass through this, if it doesn't come together, it's an all-go-home thing. It's an over.
6 green board. 5, 4, 3, 2, 1.
At the end of 1999, the Mars Polar Lander and Mars Climate Orbiter missions failed.
I don't know if you have net punched up, but the numbers reported that they think that the signal may have been due to RFI or something in the front end. We're not seeing that in any of the other spectrums, but they're continuing to look.
JPL was responsible for these missions, and that changed everything. There was a loss of confidence. What had to be done was we had to get back in the saddle. We had to get something landed on the surface of Mars. The problem was we didn't have a lot of time. We have to go back to something we know. And what we knew is we knew the Pathfinder lander. And because of that confidence, we can do it in a short time. We got to take the Pathfinder lander and stick our rover in it.
Here we go, 6 pulses for equalization at -18 dB. Pulse number 1, 3, 2, 1, mark.
We knew at the time we had a 3-year project to go to launch, and that's just very, very tight for a mission of this kind of complexity. And we've been fighting that challenge since the beginning. You worry about, am I got the right plan? Do I really have it figured out? Are we on track? Can we stay on track?
I'll briefly go over launch crews and EDL and just give you an idea of how the downlink process works during those phases. I'll spend a lot more time on surface, specifically the tactical downlink process. I'll also talk a little bit about a couple key additional requirements for Red Rover Goes to Mars.
You start getting into this cycle of things changing just a little bit here and just a little bit there, and all of a sudden the mass got heavier, and so other things had to change. Your design heritage, the blueprint, I use the phrase that I will never use again because no one will believe me, is build to print. I said, we will take the Mars Pathfinder lander and build to print. We will take the blueprints and we will send it to the machine shop, build these same things again, and that will be the shell that we land in. And then we just have to design this rover that fits inside. That build-to-print concept is the one thing that was completely wrong.
The message here is if you see something that you don't like in the MER mission system design, I'm one of the people you can blame.
I came to the realization that the heritage wasn't in the blueprints. The heritage was in the people. And the people who had designed this thing before, they've gone through this design work, they've experienced all the difficulties, they know how to solve it.
And then we have a final TCM at 48 hours out.
They tell us these only weigh 40 pounds, but they feel like 100.
We are building airbag systems to cushion a rover that's going to Mars. Well, we have a deadline to meet for testing, so we have to work a lot of hours and work hard and get it done on time and make it work good, too. A lot of it is sewing through these thick layers. It's very difficult. The stuff we coat it with makes it hard to go through. We've had to get special needles, special machines, and it takes a lot of strength to press it out with your fingers and sew it. I've done both. I've worked suit parts, I've worked gloves, and I've worked these. It's like peas and carrots, you know? Gloves are more delicate, more complicated mentally, smaller. This is physically challenging because it is heavy. We have a lot of questions because in the whole time you're building it, you're wondering, is this going to be right? Is it going to be okay? Is it going to work? You can't imagine the joy. We were jumping up and down when Pathfinder landed and was successful, and that's what we want to bring into this. How would you feel if you knew that something you have actually worked on and touched every day was on Mars? Our names are on Mars because we got to sign the lander panel of Pathfinder. And believe me, we'll have our initials in some of these scenes too.